Operation Chrome Dome demanded continuous airborne bomber patrols to maintain immediate strategic capability. This operational mandate required heavy aircraft to remain on station for extended durations, which in turn forced a reliance on frequent mid-air refueling. On January 17, 1966, a United States Air Force B-52 G Stratofortress aligned for a routine refueling contact over Palomares, Spain. The bomber carried a primary payload of 4 B-28 hydrogen bombs. The physical objective was to connect with a KC-135 Stratotanker at 31,000 feet. The procedure requires the receiving aircraft to match speed and maintain a precise spatial envelope behind the tanker. The pilots must account for aerodynamic wash and minor turbulence while maneuvering a massive 8-engine bomber into a tight contact window. The connection relies on a rigid telescoping boom extending from the tanker. The bomber must close the final distance slowly. During this final hookup, the B-52G and the tanker moved beyond the narrow, safe envelope of the refueling contact. The margin for correction disappeared. The bomber and the refueling boom collided. The impact transferred massive physical force directly into the upper fuselage of the bomber, ripping open its structural spine. At 31,000 feet, aerodynamic pressure dictates survival. The physical breach destroyed the structural integrity of the bomber. The airframe could no longer handle the flight loads and immediately broke apart. The collision also induced catastrophic failure in the tanker. The B-52 broke apart high above Palomares. The KC-135, by contrast, remained more nearly intact as it fell, then exploded shortly before ground contact and again on impact. Heavy debris began a ballistic fall toward the Spanish terrain below. The immediate operational focus expanded from rescue and crash control to payload accountability. In this type of event, ground teams had to locate, identify, and secure every nuclear device while survivor recovery, radiation checks, and site security continued around them. The stakes of the operation were defined entirely by the weapon payload. The 4 weapons were B-28FI thermonuclear bombs, commonly described as 1.1 megaton class weapons. The loss of control over even one device presented an unacceptable security hazard and a potential contamination event. The protocol demanded a seamless chain of custody from the moment the aircraft went down until the weapons were verified safe. Ground search units deployed immediately to the crash site to inventory the scattered wreckage. The heavy components of the aircraft fell in a predictable ballistic pattern dictated by gravity and the forward momentum of the aircraft at the moment of structural failure. Search teams systematically walked the debris field. They located 3 of the 4 hydrogen bombs on land near Palomares. One weapon was found in relatively good condition after its parachute cushioned the impact. 2 others were badly damaged when their conventional high explosives detonated on impact. There was no nuclear detonation, but plutonium contamination was present at those 2 sites. Teams secured the weapons and the contaminated debris under military control. But the inventory was still incomplete. The Recovery Command faced a massive operational constraint. The 4th weapon had deviated from the expected ballistic trajectory because its deployment sequence initiated far enough to release a partially deployed parachute. Drag from the nylon canopy slowed the casing, exposed it to high-altitude winds, and carried it offshore, clearing the landmass before it sank into the Mediterranean Sea. The search no longer ended at the crash zone. It now opened somewhere over water. Where did the 4th weapon drift during its descent? During the breakup, aerodynamic forces inside the payload bay pulled part of the 4th weapon's nylon canopy into the slipstream, leaving the weapon suspended through layered air. The descent through 31,000 feet of airspace forces an object to pass through multiple distinct atmospheric layers. Wind speed and direction shear drastically at different altitudes. The upper-level jet stream pushes one way while the lower-level coastal thermals pull in another. A parachute-suspended payload rides these varying currents, shifting its drift heading as it drops from one layer to the next. The engineering team did not have the exact extraction altitude of the parachute, nor did they possess the precise wind layer profiles for the exact second of the airframe collapse. The horizontal displacement of the weapon could not be mapped as a single predictable line. The operational consequence was mathematical. Search Command had to estimate the maximum distance the parachute could have carried the weapon before water entry. applying upper atmospheric wind assumptions against the known drag behavior of a partially open canopy. The modeled search box covered 25 square miles, and its difficulty was vertical as much as horizontal. Beneath the surface, the Navy faced steep underwater canyons, sharp sedimentary ridges, and deep geological trenches. Attempting a blind sonar sweep across 25 square miles of complex acoustic terrain would produce thousands of false targets. The strict time constraint imposed by national security protocols meant a systematic grid search of the entire 25 square miles was unacceptable. The search command needed a way to shrink the mathematical boundary before committing deep water assets. How could the recovery force narrow down a 25 square mile drift zone over unmapped ocean terrain? The United States Navy activated Task Force 65 under the command of Rear Admiral William Guest, but the next requirement was evidence, a physical data point that could focus the water search. That evidence came from a local Spanish fisherman named Francisco Simo Orts. Operating his vessel in the Mediterranean during the aircraft failure, he witnessed what he first believed was an airman descending under a parachute. After the crewmen were accounted for, Navy officials realized the sighting may have been the missing weapon under its partially deployed canopy. Orts could guide them toward the rough area where he had seen the parachute enter the water, though not to a modern fix with exact coordinates. The observation allowed Task Force 65 engineers to build a probability grid search that no longer treated all ocean surface equally. Instead of mapping a wide boundary based on maximum possible wind drift, the engineers integrated the localized bearing line from the fishermen with the calculated descent dynamics of a heavy mass under a nylon canopy. This mathematical intersection produced concentrated high-yield zones. The command assigned probability percentages to specific grid squares along the projected trajectory. This procedural boundary allowed the Navy to concentrate their slow underwater acoustic and visual assets on the highest percentage coordinates first, intentionally ignoring vast stretches of low-probability water. The primary high-probability grid pointed the search forces toward a hostile geological feature known as the Rio Almanzora underwater canyon. Deep water localization requires specialized hardware and a strict workflow. Surface ships, sonar systems, towed equipment, and underwater television all entered the search. But the terrain and sea state made every method slow and uncertain. The decisive clue was not a clean sonar target list. It was a long furrow on a steep slope, first seen by DSV Alvin, a manned deep ocean research submersible, and then followed over repeated dives toward the missing weapon. Operating a submersible in deep water is a heavily constrained process. The vehicle relies on internal battery power, strictly limiting bottom time. A significant portion of each dive is consumed transiting vertically from the surface to the seabed, leaving a narrow window for actual scanning. The submersible must move at extremely slow speeds, relying on exterior lights to pierce the total darkness. In mid-March, after repeated Alvin dives along the furrow, the submersible's exterior lights illuminated an unmistakable shape. The crew visually identified the missing hydrogen bomb. It was heavily tangled in the extensive nylon webbing of its parachute. The physical coordinates of the target introduced an immediate environmental hazard. The target was located at a depth of 2,550 feet. It was not resting on a stable, flat shelf. The massive casing was perched precariously on a 70-degree sedimentary canyon slope. The target was verified, but the recovery problem had shifted from search mathematics to unstable underwater handling. How does a small, deep ocean submersible attach hardware to a massive weapon on a precarious sedimentary slope? Any vehicle approaching the casing now had to work against the cliff face without disturbing the mud holding it in place. Deep ocean-manned submersibles are not heavy-lifting machines. To navigate in a three-dimensional underwater space, a vehicle like Alvin must maintain perfect neutral buoyancy, carefully balancing its internal mass against the density of the surrounding seawater. It lacks the excess buoyancy and the vertical thruster power required to hoist heavy industrial payloads. If the submersible attempts to apply direct lifting force to a massive object, the physics of reaction dictate that the submersible itself will simply be pushed backward or driven into the seabed. Extraction, therefore, required a distributed system. Alvin would place the rigging, while a heavy surface salvage ship provided the winching force through a line dropped to the target. At that angle, the casing was held in place only by static friction and the temporary compaction of the mud beneath it. Any localized disturbance could break that equilibrium. The mechanical thrust from the submersible, an accidental bump from a robotic arm, or the heavy drag of a steel cable lowered from the surface can instantly trigger a sediment slide. If the mud gives way, the massive weapon will slide down the canyon wall, tumbling into abyssal depths far beyond the operational limits of any existing recovery asset. That risk shaped the rigging approach. The operators maneuvered Alvin directly against the cliff face at 2,550 feet. Operating exterior mechanical manipulators in the deep ocean is a slow, methodical process. The crew had to constantly adjust their thrusters to counteract mild underwater currents that threatened to push the vehicle directly into the wreckage. The same parachute webbing that had carried the weapon offshore now became the usable rigging feature, because the smooth, ballistic casing offered no structural hardpoints or lifting eyes. Carefully, the Alvin crew directed the mechanical arm to maneuver a single lift line, guiding it through the heavy nylon deployment webbing. This required precise spatial awareness. The crew had to ensure the surface line remained slack enough not to drag against the unstable canyon wall, yet controlled enough not to entangle the submersible itself in the parachute lines. After hours of meticulous manipulation, the line was anchored to the payload, and the physical risk transferred vertically. The salvage ship USS Hoist began to take up the slack, bringing the weapon clear of the slope through one improvised parachute connection that still had to survive the long pull and the violent shallow water zone. What happens when the static strength of a single hoist line meets the kinetic energy of the ocean surface? A static mechanical cable rated for deep water deadweight faces a severe mechanical trade-off when it interacts with the dynamic kinetic energy of ocean surface waves. The single line rigged to the weapon on the steep canyon slope held firm as the heavy deck winches on the surface vessel began the long vertical pull. The deep water environment is largely static, insulating the suspended payload from turbulent motion. Throughout the majority of the ascent from 2,550 feet, the tension on the hoist line remained constant, bearing only the combined mass of the weapon, the soaked nylon parachute canopy, and the steel cable itself. Near the surface, ocean swells move with enough kinetic energy to turn the salvage ship into a giant buoyant lever. When a wave pushes the ship upward, the vessel pulls abruptly against the suspended line, creating a snap load, a sudden spike far above the static dead weight of the object below. On March 24th, the winch systems pulled the weapon upward until it was positioned exactly 50 feet below the surface of the Mediterranean Sea. At that depth, a heavy surface swell lifted the ship and overloaded the improvised connection. The first lift failed at the worst possible moment. In heavy seas, with the bomb only about 50 feet below the surface, the improvised connection lost its hold and the lifting line snapped. The weapon dropped back into the water column, plummeting into the Rio Almanzora canyon. Falling blindly, the heavy casing bypassed its original resting location. It slid further down the 70-degree canyon grade, finally coming to rest roughly 300 feet deeper, at about 2,800 to 2,900 feet. The failed lift erased the progress of the initial deep water rigging phase and forced Task Force 65 into an operational reset. It now rested closer to the unrecoverable canyon floor. The operational command immediately pivoted their objective from extraction to absolute localization. They could not risk the asset sliding further down the incline while remaining completely untraceable. On April 2nd, the command deployed the deep ocean submersible once again to relocate the heavy asset. The crew successfully reacquired the target at the deeper site. The weapon had to be recovered before current, slope failure, or another failed approach could move it beyond reach. The command now required a new extraction plan. The failed shallow water lift proved that a single improvised line was not enough. Manned submersibles could help find and inspect the target, but the heavier grappling work demanded a surface-controlled system capable of placing redundant hardware without putting a crewed vehicle into the handling load. How could the Navy secure the weapon? The engineering team turned to the cable-controlled underwater recovery vehicle, designated as CURV-1. This uncrewed tethered machine was originally designed to recover test torpedoes, not nuclear weapons, from a steep submarine canyon. To reach the hydrogen bomb, the Navy pushed the vehicle into an extreme recovery roll near the edge of its depth capability and adapted the operation around that limitation. CURV-1 brought its own handling constraints. A thick umbilical tether connected the machine to the surface vessel, supplying continuous electrical power and transmitting lifting force while keeping human operators out of the high-pressure hazard zone. In deep currents, the surface vessel had to hold precise position so the cable would not drag the vehicle off course or foul its thrusters in the debris field. Operating from the deck of the surface ship USS Petrel, the remote pilots navigated CURV-1 down the descent path, homing in on the acoustic pinger signal. Once the vehicle reached the canyon wall, the old rigging problem remained, but the failed single line had changed the requirement. The final connection needed redundancy. Specialized grapnel hooks would be driven into the tangled risers, spreading the load across the nylon and giving the final connection redundancy. This accepted the risk of tearing the fabric in exchange for multiple holds on the parachute system. The CURV-1 operators manipulated the vehicle near the thickest bundles of parachute material and worked to secure grapnel attachments into the tangled rigging. The plan called for 3 separate grapnels, but the operation did not unfold cleanly. By April 6th, the remote vehicle had secured 2 grapnels, and the parachute itself became part of the final connection as it tangled around CURV-1. That entanglement was dangerous, but it also gave the recovery force one last physical hold on the bomb. Once the bomb, parachute, grapnels, and CURV-1 were bound together, Rear Admiral Guest accepted the risk of raising the entire entangled system. The deck winches on the USS Petrel engaged. The lift carefully pulled the asset clear of the seabed, not because the geometry was clean, but because the tangled connection held long enough to move the bomb upward. At about 50 feet, divers secured the weapon in a bridle, giving the final lift a safer load path than the failed single-line attempt. On April 7, 1966, the intact nuclear weapon was hoisted out of the Mediterranean Sea and secured aboard the USS Petrel. This successful deck recovery concluded an exhaustive 80-day campaign and set a new operational benchmark for deep ocean forensic recovery.